I always find the last class that I do with people is, out of fairness sake, nothing that you have to do anything in your last assignment with. So there's no content here that has anything to do with your assignment. You don't need any of it. And so it's a little shorter because typically people have questions at this point, and I like to have a little bit of time to let you throw the questions out. What we do like to do is set up next term. And next term, we're going to take the next step forward, and we're going to talk all about web servers. So I'm going to tell you all about them today. We'll reiterate a little bit of it next term, and then we'll start building them. So
we're going to hear the same thing?
You're going to hear a little bit of it. I'm going to do most of the theory today, right? And try to make it.
Set up web servers?
You already have some stuff set up. You just don't know it yet.
But like exactly coding in servers, like
Yeah, that's what we're going to do next term. Not today. Not today. Right? There's too much to it. Right? When we talk about web servers, we want to make sure that we're clear that what we've done so far is what we call the client. It runs on the browser, and the browser's on everybody's desktop, right? Where did that stuff come from? Well, when you typed in a URL, you got it from somewhere. You got it from a server. As we test, we set up a test environment locally. So the server's running here. That's what that live server is really just doing. It's just serving files, just giving us files. Next term, we're going to take it a step further. And what we're going to do with it is we're going to expand it out into not just serving files. We're going to expand it out to the point where we're going to set up communication between our client program and our server program, and they're going to stay talking to each other. Now, first, we're going to do it in a very traditional way, okay? And hopefully, at least by the end of term 3, we're going to be doing some kind of non-traditional stuff with it. We're going to progress from learning what the client and the server do, building our own servers, to building a more elaborate client-server application, game, to the point where we're starting to build what typically in game engines these days is done 100% on the server side. Okay? So the way that games typically use this stuff these days is that they typically track information on what players are doing. And how do they do that? Well, they send information to a web service. And that service records that information. It doesn't just record the information, it also provides an administrative interface and charts and graphs and some analysis of what's going on. And you can even set it up to the point where your game is running on a bunch of different clients and they're publishing information to this web server. If you set your server up nicely, you could have it so that an operator sitting on a web page can move a slider, and every new game that starts up gets that new value as an initial value to start. Now that's kind of cool to start with. What if we kind of turn it into a feedback loop? And we get to the point where, and we will talk about this when we do some emerging tech stuff, from an artificial intelligence perspective, my game clients are out in the world, and I'm tracking what they're doing to one of these web servers. And I'm analyzing what they're doing, running some machine learning algorithms on it to come up with new and better strategies to play against. And then every new game that comes up grabs those strategies from the server. The game now is learning. The more players that play, the smarter it gets. Okay. Now that stuff doesn't happen in real time. It's too slow, and we need to collect mass data. We also have a web server architecture that allows us to expand. If you play Call of Duty, how many players can you get? 64? 32?
Around that.
Around that, okay. You play Clash of Clans, how many players can you get simultaneously? About 10 million. Okay. There's a scale factor there. And that all has to do with the way the apps are architected. So we're going to dive into the architecture that gives us 10 million players. Right? And it all starts from the stuff we were talking about the other day, which is, long, long ago when we had computers that we wanted to talk to each other, they had to be the exact same kind of computer, and some programmer had to write a program that opened up a connection from one to the other, and they need to be physically on the same wire. As Unix started to pervade, the network we know today started to evolve. And people kind of saw that this addressing and port number thing was really the best way to lay out networks. And all computers started to learn to talk this same language. And that's where all those layers I was talking about got pushed down into hardware. And this is common in software development. You build something new and innovative. You build it in software. It's flexible. It's configurable. It starts working. It starts to become boring and mundane. Becomes brittle. You can't touch it anymore without breaking it. And at that point, you're like, look, no one's changing it anymore. Let's bake it into hardware and move on and do something more sophisticated. So a lot of that's what's happened with the communication between computers these days. The software part has become so boring and mundane, so easy to do, that we've baked it into a lot of the hardware. So we've made a lot of the software easy to do. Now, of course, everybody wanted to do things the same way, and everyone wanted to fit into a nice structure. So, like I said, the protocol guys showed up, the standards guys shows up. Mostly these are electronic engineers who decide that everybody should do things the same way so that things are interoperable. The upside is things are interoperable, right? IBM computers can talk to Macintoshes, can talk to Linux machines. They don't care. The downside is standards don't move quickly. So this kind of slows the whole process down. The way this all works, very much like I was talking about the other day, from our programming perspective is, to make two machines to talk to each other, you need to know their IP addresses and their port number. They can each open up a connection to each other. All of that gets routed through what we call the internet service on a Windows machine, or INetD on a Unix machine. Now, as a little sidetrack, all of the Unix machine terminate and stay resident programs, those services that run in the background, are typically called daemons. We got little daemons running around in the background. That's always been a play on words. You'll find that in all Unix things. The internet daemon that runs in the background is something that developers have control over. And the Windows internet service, except on these machines here, typically programmers have control of as well. There's a configuration setup here, a bunch of configuration files. When you start the internet daemon, it reads the configuration file. And what the configuration file is a list of port numbers and programs. When someone tries to connect on this port number, I run this program to answer. So the biggest one that we're interested in here is on a Unix server, on a web server, port 80 and port 8080 are mapped to the web server. What web server are they mapped to? Right? Well, there's two real big ways that we run web servers these days. There's the way 90% of the internet still works, and there's the way we're going to do it. Right? Because the way that 90% of the servers work, nobody's building this stuff this way anymore. It's all legacy and historical stuff. It's there because no one wants to tear it down, not because it's better.
And not break the internet apart. Not break the internet. Like
Yeah.
The old version.
And it's the typical kind of progression of new technologies, right? Things start off and nobody wants to use them. They're what we call the bleeding edge. It's painful, it's not well thought out, there are bugs, people have to figure out how to make things work. As more and more people jump on and early adopters start to gravitate towards that new software, it starts to solidify. It becomes robust, it becomes stable. right? Like open source tools, they become more robust because you've got thousands and thousands of people contributing and fixing bugs. And these things then become kind of the de facto standards before the standards guys come in and make them the official standards. In the meantime, there's some old technology that you're typically replacing. And that stuff starts to grandfather. It starts to stagnate. Nobody's working on it anymore. It doesn't get any better. Okay? We have that exact situation going on right now with the internet and the web. There is a de facto standard web server, a piece of software that these guys launch called Apache. And the Apache web servers are running on all of the major internet domain hosts. To use as an example, if you want your own web service, you go to GoDaddy, right? Now, GoDaddy is registered with the Internet, the authority that manages the internet. And they have the authority to register domain names. And there's a couple requirements when you register a domain name. You need to have that name be unique, and you have to, in the routing tables for the entire worldwide network, have an IP address to make that domain name land on. They need to register that when I go to myfavoritewebsite.com, it goes to a specific IP address. So part of the reason that a company like GoDaddy exists is you say, I want myfancydomainname.com. They go check out whether that name lists and exists in the registry anywhere. And if it doesn't, you can have it. And for a small fee, they will take one of their computers, assign it an IP address, and register your domain name against that IP address so that when someone looks it up in the internet, the IP address part, they get an actual real live IP address. Okay? That's why you have to register them that way. And then what does GoDaddy do? GoDaddy fires up an Apache web server hooked up to your IP address and port 80, and then maps it to a folder on their server, on their computer. So now whenever somebody tries to go to mybestwebservice.com, it goes into the internet, the routing tables give it the IP address that GoDaddy figured out. It hands it back to the person trying to connect. They try to connect to that IP address and port 80, which connects to GoDaddy's machine, which is running Apache, because the internet daemon says, hey, when this IP address port 80 gets a request, fire up Apache. The Apache web service looks in a folder and sees if your request is ready and hands it back to the client. Okay? It's super high level, but that's really how the internet is working. So all of this kind of stuff, we don't really care about. I mean, it happens and it's fascinating and it's interesting. We don't control it. We don't use it. We don't care about it. What we care about is the part I just talked about. What we care about is, I'm here on my computer and I typed in a domain name. And what happens next, and what do I control as a developer? Well, as a developer, this IP address gets routed through a gateway, out through a name server, out to a top-level domain name server that figures out your IP address. It figures out your port number. It makes a request. Hey, whatever's listening on the far end, I want index.html. Give it to me, right? That server has got to be sitting there, waiting, running, and hand you back that file. Okay. Now that's great for just serving plain old HTML pages. You can probably get away with some CSS files that way too. You can load some JavaScript files that way. Okay, that's nice. Now I want to write some data in a database. What do I do? And that's where we're going to go next term. We're going to start to build not just that web server that serves files out on the server. We're going to build a piece of software there that does exactly what we want it to do. It listens for special messages that we want to send it. And it's going to do work on that remote server for us. What kind of work? What kind of things do you think the server would do for you? I mean, there's a couple obvious ones. One is serve out web files to millions of people. And the other one I've talked about, which is store data in a database. Well, what else would that server do?
You read messages, you message someone, you go to the server, and
Yeah.
the server sends back a message to somebody else.
Yes, the server can definitely talk to another server. So if you have some long computation you want to do, you could set up 2 or 3 servers so that you contact the server and the server contacts another computer somewhere out on the network to do difficult work. What else could you do with it? Something we're not going to do, but authentication, right? You log in, you use your Google. Well, you're not connecting to Google when you log into that server. But it says log in with Google. Well, what's happening? Well, the server is connecting to Google, taking your credentials and handing them off to Google and say, is this a person? Is this a real person? Is this the person who says they are? Right? Well, Google has a whole server dedicated to you being able to talk to it. And the trick with all of this stuff, this ability to hide and manage data, to do some complex processing on a third server, right? Some machine learning or artificial intelligence stuff. Or maybe you have some sensitive data that you don't want to expose or share somewhere. All of this stuff is stuff that you may not want to put on the client machine. It's also stuff that it might be advantageous to have in one central location. And depending on what we're doing, we have to decide what part of our application goes where. Now you hear some weird terminology around this, and if you've ever heard people talk about thin clients versus fat clients or thick clients, what they're really talking about is where the processing is happening. A thin client, the user interface part, the part in your browser, the part on your computer, is doing almost nothing. It's a user interface that's collecting information and sending it all off to a remote server. The downside of that is the server has to be big to be able to handle lots and lots of people simultaneously. Right? The upside of that is all the stuff's in one spot and it's controlled. Once it's on the server, it's not like the internet in general can see it. They have to get through all of your security hoops to get into your data and know how you've stored things and how you're managing it. On the other hand, if you hear things about like a fat client, what you're talking about is some application that runs mostly on the local computer. All the heavy lifting and computing is done on the local computer, and very small amounts of things are stored or computed on the remote server. Now, these days, the fat clients win pretty much hands down every time. And you think about why? Right? How powerful is this machine? Like, you want to compare it to what? A supercomputer of the 60s that took up a room this size? Because this thing can outperform it. Right? In fact, your phone can outperform a supercomputer of the 60s. So these clients actually have so much computing horsepower. I've shown you time and time again when we bring up Task Manager how heavily loaded your CPU is, right? So you got lots of CPU to spare here. You got a little bit of memory to spare, generally, unless you're a developer. And even as a developer, I would bet that you don't really notice a slowdown if you run Photoshop, Substance, Maya, Unity, Unreal, Visual Studio simultaneously. You could probably even load a project in Unity, Unreal, and Visual Studio and tell all 3 of them to compile, boom, 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 and not really notice a slowdown on your computer. You get upset if some other app doesn't come up instantly. Just remember, there was a point in time where when we pushed compile, we walked away for 20 minutes and got a coffee because it took the computer that long to build something. And during that time, the computer was pretty much 99% loaded and was unresponsive to anything else. when we want to connect and talk to things, we want to really just do three basic things as a programmer. I want to know what I'm connecting to. I want to make a request. Hey, do this for me. And I want to get a response back. Sometimes the do this for me is go fetch me something. So I want to get some information back. So I need to be able to deal with that. The fun part about doing this on the web, we try and make these things easy. The not fun part about doing this on the web is that they're 100% what we call asynchronous. If I make 10 connections and requests, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I have zero guarantees I get the answers back in the order I made the requests. I can get the answers back in any order, and I have no knowledge ahead of time of what order I'm going to get things back in. I just have to cope and deal with the fact that I asked for 10 different things and I got number 7, number 2, number 1, number 9, number 8, number 6, number 4 in that order. And that the next time I ask for those 10 things, I get them in a completely different order. There's no sequencing to it at all. On the server side deals with one request at a time. And typically the way Apache servers do it, as much as it seems like a really big deal to build a whole program that deals with these requests, that Apache server gets an entire copy of itself started up for every single request. Lots of copies of that Apache program, which means the machine it's running on, the server, can get overloaded very quickly. Have you ever heard stories about denial of service attacks? DDoS attacks. You've heard of them. You know what they are? How do you create them?
You make a lot of requests to the server.
You make more requests to a server than they can handle. And why did DDoS attacks kind of die all of a sudden? They were completely unsuccessful and have been for a decade now.
Because they stopped copying?
Because the guys programming the server said, I'll handle 100 requests and then I'm just going to ignore everything else. I'm literally going to throw it away. Right? Well, this isn't great if you're the guy trying to run a service. Okay, so you can still mess with people's servers. But typically, if you fire too many requests too quickly at it, it'll throttle itself and say, yeah, no. If it's really good, it'll buffer them and deal with them when it can. So from the client, I want to make a connection. I want to say, I want to connect to that server. There's a great bit of power that comes with this as well, which is once I can connect to my server and I know how to talk to my server, now as a developer, I can create a service and I can publish that service out there on the internet. I can say, hey, anyone who wants to use my service, just connect to this IP address and this port number, and then here's the way I want you to make requests from my server. And I will provide information for you. Can you think about who does that? Who provides services that you can access remotely?
AWS.
AWS, perfect one.
Azure.
Google, Azure, yep. Facebook, and a host of other services that we'll dive into a little bit. So I like to think of some of this stuff when we're talking to servers and learn how to talk to web servers as kind of a gateway drug. Once you can talk to one thing, your whole world opens up about the number of services you can access from your application. I'll also point out, how much have I talked about JavaScript? Can this be done only from JavaScript? No. This can be done from any programming language. Okay? JavaScript is by far the easiest to do this. And there's a couple reasons why we'll get to. Okay? In every single instance, we make a connection, we fire a request, the server will handle it, and it will take some time. We don't know how long. And when it's done, the client will handle a response. In the meantime, what does the client do? Well, the client has to go back to running. The client can't just lock up and wait for a request to come back. It might be 100 milliseconds. Right? And if we're building a game, 100 milliseconds is an eternity while you wait for some little piece of data to come back. So you want the client free to continue running. It's going to fire requests out into the internet all day long, doesn't care. And they're going to come back who knows when. And when they come back, I'm just going to deal with what I get. Okay. It's really easy to talk about how you understand that asynchronous part. When you start programming it, it gets a little bit more dicey. Right? So, we want to be able to do that in a nice, easy way. And this is where the internet and the web came up. So, it's back in the 1980s, and as we start looking at information, I've probably told you the story of Tim Berners-Lee and how he was doing his academic documents and decided, hey, I want to distribute these in a more robust, easy way. Now, what he had to come up with his grad students was, technically, how is that going to work? And what he came up with was, we're going to do a couple things. First of all, we're going to cross-connect the client and the server. Just like we were showing in the iOS class where you could pipeline command line programs together. We're going to take the standard input on the client and we're going to feed it from the server. So whatever the server writes to its standard output device, instead of going to the screen, we're going to redirect that into the client. Which means we're going to write some text out here. On the client side, whenever we want something, we're going to write it not to the standard output device, but to the connected server. And we're just going to write some text. Now that makes things a little bit nicer because we're just sending text back and forth. Right? Now the downside is we got to take that text apart and parse it. But the upside is the connection part gets done. When I connect to a remote web service, particularly when I'm in the browser and I type a URL, that identifies the server uniquely, IP address and port number. And the rest of that URL is just a folder path on that machine. So I've already made the connection when I do that. So I'm just going to take advantage of that connection, and I'm going to send a message that's built out of text. And he came up with a really simple format or protocol for that text. It says we're going to send a single blank or a single line of text that gives us a request. And then we're going to send a blank line, and then we're going to send another chunk of text. And we'll tell you how big this is, but it could be anything. And it's up to the server to interpret it. Okay? And this is where you, the programmer, comes in. How do you want to interpret it? What do you get? Now, there are some conventions we've developed about how we send this data and how we format it so that on both the client and the server, we are talking the same language and convert it back and forth. But when we start talking about a web server, we are, in effect, doing this. Now, there's some parts that happen automatically, right? Certain requests that you make of a server that the server just answers on your behalf. Those particular requests typically involve things like getting HTML files. So most servers are set up so that the default file is index.html. When you enter a URL in your browser, you don't type index.html, you just have a full folder path, right? And then a slash on the end or no slash on the end. We don't care because we're smart enough to figure that out. And what the server is actually doing is it's taking that full path, it's appending index.html and going for it. And then inside the index.html, we're using relative paths. Relative to where that index.html is on the server, go find me a CSS file, another CSS file, a JavaScript file. That's great for retrieving stuff. At some point, we're going to want to send information to the server that we want kind of hidden. And that's what we're going to do next term. We're going to build our service up to do specifically that thing. So we got to figure out, how do we send these responses? How do we get a response? Right? And then how do we do something smart with that response? And when we first start building these things, we're going to want to do it on the local machine. I want to put the client and the server on the same machine. And that's purely for speed and debugging reasons. I'm not assuming my server is going to work. Right? On top of that, I was talking about that transition into different kinds of technologies. While the Apache servers are there, the programming side of those Apache servers is through a language called PHP. And PHP is a pre-processing language. In other words, if you ask for a PHP file, what the Apache server does is it goes and finds that PHP file. It runs it through the PHP interpreter, which generates an HTML file, which Apache sends back to you. This is how Moodle works, which is why Moodle is slow. You change something in Moodle, takes the whole page, sends it to an Apache web server. The web server interprets the page, creates a new PHP page that it wants with new data in it, runs that through the PHP interpreter to generate a new HTML page, and then sends you a whole new page back every time you change something in Moodle.
So not this small part and change it.
Oh, no, the whole page.
Okay. So that's why we're doing different from.
Right.
Okay.
So, as you probably imagined, we're going to use Node.js. Now, the thing with Node.js is one of the components of our browser is the JavaScript interpreter. And the JavaScript interpreter is an open source project, and everyone uses the same one. It's called V8. And at some point, a few folks on the open source community said, you know, I kind of want to run JavaScript, but I don't really want the browser. So what they did was they stripped V8 and they built a shell around it so they could run just the V8 interpreter on its own. That's what Node.js is. It's just the JavaScript interpreter. Well, that doesn't get us a web server. That's just JavaScript running in a command line or an environment. But that open source community started to build more and more components. And one of the first things people wanted to build was something that mimicked the Apache web services. So they started to build components that when you install and link them together, give you the equivalent of the Apache web service. It means when we build our web servers with Node, we're going to have to replicate everything that Apache does. So when you get index.html, that's no longer automatic. You got to write your own software to go find, fetch, and retrieve and send back to the client index.html. Right? That's not that hard, but you got to do it. You got to take care of that. And in fact, what we'll do is we'll build kind of a generic server-side module that takes care of all those static files, those things that don't change. So any one of these things, if you want to get one of those static files, this piece of code will handle it and it'll just go fetch the file and send it back to you. For those things that aren't static, we're going to have to write our own code to do our own thing. That also means we're going to have to write a client application to test it. So we're going to build next term a game, and we're going to build a client server game, and it's going to have a couple components to it, a part that runs in the server and a part that runs in the browser. And we're going to do it in two pieces. We're going to do one part of it solo, and the other part of it we're going to do in pairs, because the game part of it that we're going to do is far more complicated than Minesweeper, right? And that thing that stands in between that server, well, whatever we write as the first assignment will be the server for the second assignment as well. Right? So when we get together in pairs to put together the actual game, one, we're doing that because we'll only have 3 to 4 weeks to build the game. Because we're going to need 3 to 4 weeks to build the server. Okay. The second part is when we're building a more complicated game with multiple people, we're going to need some source control to make sure that we don't step on each other's toes. And the upside is if we all build the server side to the same specifications, then I guess all the servers will be interchangeable, right? I mean, if 6 people wrote the same software to do the same things, they'd all be identical, wouldn't they? Not a hope. Not a hope. But this is part of the challenge. I'm going to give you a specification, and every one of your servers is going to need to be able to manage and deal with that specification. How does the data fit together? Right? And it doesn't matter if you do it a bunch of different ways. As long as you can deal with that data in a consistent way, and all of the servers can, then they will be interoperable. And we'll put those pieces together. Then, when you get into your teams, we're not going to form the teams till halfway through the term. When you form the teams, you get to sit down and go, well, whose server do we use? So you get to look at each other's code and go, well, mine's a piece of crap, so we're using yours. And then you'll be like, well, no, mine's a piece of crap, we're using yours. Right? Now, hopefully you're smart enough not to just rewrite it at that point, because that would be really time consuming. But if you do it right, then in the span of the first 3 weeks or so, yeah, that's right, you can write this whole server in 3 weeks. You're going to have a server that you can then reuse as you build the game part. Okay? It'll be a good challenge for you. You guys haven't been challenged enough yet. Right? I can make it more challenging. No thanks. We're not there yet. Wait till we do the 8-player multiplayer simultaneous players game.
Can you spoil the game that we're gonna make? Spoil?
I'm going to hold on to that info until...
Okay.
Yeah, I got to have some secrets left. Great. So, when we get this set up, I don't know how many of you have played. Do you like doing your web stuff in Visual Studio, the full thing, or do you use Visual Studio Code? Code?
Yeah, for this one, so yeah.
You can do it in either. It really, really doesn't matter, right? You'll notice in both of them they have debuggers, and the debuggers will work with the web stuff. You'll also notice I don't use it, right? It's not that I don't like it and I don't use it. I don't use it on the client side. I don't use it on the client side because when I start doing this, I do need a debugger for the server. And I can't run the browser debugger on the server because it's on the browser, which is the client. So I need a debugger I can run somewhere. So I've been holding on to that debugger in Visual Studio Code because I use it on the server side. Right? I can still edit the client code in it. I can edit the server code in it, but I can debug the server. When we debug the server, and we'll walk you through setting all this up, we have to do a few extra steps because, like I said, these things are not synchronous. You're not going to get the messages when you think you're going to get them, but when we're debugging them, it's kind of impossible unless we can make them synchronous. So we have to do a couple little intermediate steps. When we build our local test server, so that when I go through the client and send a request, I need to stop the client in the debugger.
Until the information gets back.
And then I need to step through it on the server sequentially. I need to force it to be sequentially. And when it sends a response back, I need to then restart the debugger on the client side to see, did I get what I think I'm supposed to get, right? Now, if we do it right, it's fairly straightforward. When you add 30 different requests flying around like this, it may get confusing. Just a little, okay? But the confusion's not in the computer's part. Just keep that in mind. The computer is not confused at all about this. you might be. Right? Where did this come from? How did it start here? How come it's executing here and not there? How come my data isn't going where I think it's going? How come my data is not there, and then all of a sudden I get an answer, and then all of a sudden my data's there, but I got the answer already, so I can't get the data. So, right, those kinds of things are going to show up. We're going to build and simulate this server locally. So just like that live server, the live server is just a static file part. The one additional thing the guy who wrote the live server did is you pointed at a folder, right? And if he sees any of those files timestamp changes, in other words, they were saved, he reloads the page. That's pretty much all he's doing. Okay. We're not going to quite do that. So we're going to add some additional tools that add that capability in without us having to write it. Right? Which means we're going to get kind of deep into the Node. How does Node do this? How do you add components and modules? How do you choose the right things? Because like anything these days, it's not like there's just one component or module you will add. There's 40 different people's variations on the best way to do this. And one of them is genuinely more popular or more robust or more stable than the others, and we need to find that one and use that one. Right? We need to use the same one that everyone else typically uses. There's an extra step to this process as well, and that is if you want to deploy these applications, in an Apache environment, you just take the client code and the server code, the PHP code, and you just drop them onto the server. Just FTP the files up there and you're done. With a Node installation, you got to do extra work. You're going to have to take the Node server and generate some static code or have a Node service running on the remote environment. So that's, again, if you go to GoDaddy, you get a control panel. Once you set up your domain name, you'll have to tell it, oh yeah, I want you to run a Node server on this folder. And here's the JavaScript server program to run. Okay, and then it'll run the interpreter on the local, on their machine. So deployment is a little bit more complicated. Okay? We're not going to do a lot of deployment. Obviously inside VFS, the firewalls that are here, right? And some of those firewalls I like, right? The firewall between us and the outside world, right? We should be able to see the outside world. No one in the outside world should be able to see us. The firewalls I don't like are the firewalls between us and the outside world. IT in VFS has put those exact same firewalls between game design and programming, between programming and sound design, between sound design and art, between art and 3D, which makes it challenging to share stuff between departments that should really just work together. So occasionally we'll punch some holes through those firewalls, but the IT guys don't know that I know how this works. All right. The last part, if you want to try this out, and I think there's a thing in Moodle. Yes, there is. We'll see if it works. If you go to Moodle, I think the little curl tool that's there is just an executable you can download and run. So there's a command line tool, command line URL, curl, CURL, and you can use it to try and see how the requests get sent to remote servers. This is going to send a command line URL, just like typing this on the browser. But if you do this on the browser will just show you a white page because there's no HTML file there. If you send this command after you get curl installed, it'll show you the kind of information you get back. And of course, we're going to have to parse that information and do something intelligent with it. So give that a try, and then we'll take a short break. Right? It's like 10 minutes or so. Get up, stretch, go get a coffee. We have the luxury of like kind of what I think right now is the nicest classroom. You don't have those stupid monitors on posts, and you have some space.
There's 6 of us.
We'll rearrange the tables eventually so that there's a space in the back to like do work, so you don't have to sit in front of the same place all the time. That whiteboard is definitely going to get used. So I'll let you give that a try, and we'll take our short break. resttesttest.com? I think the link's in Moodle as well. And you can use that to try out, again, that same URL. This is exactly the same URL, and if you just make the request, it gives you back some junk. Headers, content. Right. Now, this site doesn't return anything, but almost all web services and large sites have some sort of web, what we call a RESTful API. And these RESTful APIs, and I'll tell you what REST stands for in a bit, allow us to make these kinds of requests that we call AJAX requests to these services to get information from them. Now, if you think about it, one of the other ways you can take advantage of these is think about, like, how would you do a support chatbot for your game? Where do most people talk about and complain about their games?
And those ones. That's text of the user that sent to the server, right?
Yeah, but through services like Reddit or Discord,
Oh,
right?
Yeah, makes sense.
So if you know these key terms, Discord REST API, once we learn how to communicate client to server, we now have the ability to go into any kind of service, see if they have an API that we can access from our web client, and access it. Now, we can also access this from the server as well. Right? We make these requests from either the client or the server. But you'll get an idea of just how much information is available to you. Teams, threads, channels, creating bots. Okay? Something that we'll discuss a little bit, term 3, term 4 is, so you want to do support. You want to have live feedback. Well, let me ask you this. Has anyone ever been to an auto manufacturer site? Ford, GM, Chrysler, Nissan. Go there, try it. Right? You'll find a little customer assistance person will pop up. Same with Shaw, same with TELUS, any kind of these services, right? That little customer assistance person, are they real? Are they live? Well, the easiest test for that is go to one of these sites at 2:30 in the morning. And amazingly, they're alive and perky and answering your questions. I'm a live chat assistant. I can help you with your response.
Why
Really?
did that get work?
Right. Now, if I translate that into, so I'm an 8-person indie developer building a really cool game. Do I have the budget to have 3 people working round the clock for customer support after I launch it? No. But I probably have a smart enough programmer that builds me a chatbot that answers the frequently asked questions and has a stock answer like, wow, we don't know that right now. We're going to refer that to a more senior customer support service who will get back to you. Right? And then you get this filtered list of, the 10 real questions that you got to deal with. So you just saved your entire team a pile of money, time, and effort by building a slowly growing frequently asked questions list that lives on your server that your chatbot hooked into Discord automatically references. Someone asks a question, you go check your server against the frequently asked questions. Yes, there's a response. Yes, I return it. Yes, I make the chatbot spit it back out again. Right. So this is how we take advantage of some of these tools to be able to build the application part or the infrastructure part around the games that we build. And it's kind of the reason, if you look at the whole VFS program, why we do, C# goes to Unity development. C++ drives into Unreal and blueprints and Unreal development. So why the hell do we do the web and the mobile part? Well, the web part is so that we can get to the server. Getting to the server means being able to see what's going on the server. That means we need a client, and being able to manipulate some of these server-side services to build kind of the back end. And the example I use for it all the time is Kabam, down over here somewhere in Vancouver, has a 300-person team, and about 100 of them work on their main money-making game called Contest of Champions, which is a mobile game. Contest of Champions downloads everything every time you start the game. The list of every asset, the list of all the accomplishments you've had, your characters, their current status, your matches. In fact, of those 100 people working on that team, 25 of them work in Unity on the user interface that you see on the game. The other 75 work on this stuff. Right? That's the breakdown of where people work in games these days. Most of the hard stuff is done on servers offline or done through live operations. When they want to do the Halloween bonus campaign, well, how do they do that? Well, the game downloads every skin and every configuration bit whenever they start up. So all I have to do is go to the server that they're loading that from and change the data. Right? And I don't really want to hand over controls to live databases and code to a whole bunch of game designers at all. So I'm going to build them an interface that doesn't let them mess it up. And that's going to be a web tool. So now that game designer sits down with a marketing person and they get into my web tool and they come up with the messaging, where to upload the art, what kind of things are going to be available, bonus packs, things for sale, what to put in the item store. That's all through my web interface. And when they push submit, it probably also has a date it goes active on, and they can track extra metrics on it and see who's using it. Now, all of this stuff that happens in your browser, really, we're following this protocol, this hypertext transfer protocol that Tim and his team put together. And it kind of breaks down into those 3 chunks of text we're going to send. The first chunk is, what do I do? And the second chunk is an empty line, and the third chunk is free-form kind of data, a bunch of strings. Well, the browser initiates a bunch of these requests, okay? And the trick here is that the kinds of requests you can make, that first line, really distill down into 4 or 5 key things you can do. And those things are pretty well defined. You can get stuff, you can post stuff that I'll get into, you can delete stuff, you can put stuff, right? And that's kind of it.
What's the second again?
Post. Okay. So the get means go fetch something. And 99.9% of the time, it happens automatically and the browser does it for you. Get index.html, get style.css, get index.js. Okay. The delete is triggered from JavaScript. You send the delete message to delete a file. And most services, and yours included, are going to take those delete messages and ignore them, because we don't really want to give permissions or access to anyone else in the world through any sort of programming interface to delete files from my server. So it's there, it's possible, you can intercept it and do something intelligent with it, but for the most part, we intelligently take it and go, yeah, you're not allowed. The same with put. Put is I want to upload something. Right? So I'm going to upload something. Yeah, I'm going to upload something. Until I start to upload it, I don't know how big it is. So I generally turn that one off too. I'm not going to let you upload 67 terabytes of data in a single zip. That's going to kill my server. So instead, I might make you send half a dozen requests first, telling me what you're going to upload, how big it is. And when you tell me how big it is, and I allow you to put it on my server, I'm also probably going to truncate it. In other words, as soon as I hit the number of bytes you tell me it was, I'm going to stop. So you better fit in the size you say you are. So just security things, right? That leaves the post thing. When we get files, the interesting part here is this protocol says we can specify what we're getting. And it's sent in what we call clear text. So the request is just sent as text, which means anybody who's listening anywhere between now and our server, right? Every request is going to go out to multiple servers until it gets to the top level domain and back in. Any of those people along the way get to see all the parameters we're getting. Which means you're not going to use a username and password when you get stuff. The post is for exactly that. If I want to send a chunk of data and you can't look at the data, then I'm going to post it to the server. Specifically, the post is for me to send textual information to the server I want hidden. Both the get and the post can return things. Typically, the get returns a new file, which is why the browser handles it. And the post, I need JavaScript to handle. So, getting things, we leave to the browser. Posting things and getting an answer, we handle in JavaScript. So that's another thing we're going to need to hook up and set up in JavaScript. Now, the reality is it doesn't actually work that way these days. There's a thing called HTTP2, and HTTP2 takes all of your messages and encrypts them, and it compresses them, and it leaves the connection between you and the web server open, because setting up and tearing down that connection is slow. So for performance reasons, behind the scenes, that low-level protocol stuff that gets handled in hardware does some things that are slightly different than the way this functions. But from a programming standpoint, we don't care, because that all gets handled in hardware and it's invisible to us and we can't control it. So effectively, we're going to send text messages to post information to a server, and we're going to get some response back at some time in the future. And the rest of our work is really just, as we look through this kind of way, I'm going to send a message asking for a universal resource, some CSS, some image, some HTML. I don't have to have always index.html. If I have an anchor link that loads another page, that anchor link sends a GET request. When we get into talking about performance, every request has a cost to it. So if your page, your site, or your CSS has 3,000 images in it, that's 3,000 GET requests. Which is why we start to do some more sophisticated stuff when we start playing with web images, which we're going to talk about next term, where we compress them all into one big image. Request the one big image, but now I've got this problem of on the client side I have to do some math, right? I created this one big image, which is a whole bunch of little tiles. I now have to figure out which part of which tile goes where. But we'll take care of that. It turns out these computers are really good at doing math, and they're really pretty fast these days, especially when we can use the accelerated graphics hardware. They do that kind of stuff well. The other thing you might run into is that same origin domain policy. This is a security feature, and it truly is a feature. It means when I'm on a client, that client came from some server, myserver.com. That client can now only send messages to myserver.com. Otherwise, you get what's called a CORS, C-O-R-S, error, or Common Origin Domain Policy error. Okay? In order to get around that, you need to own the server, you need to control the server, and in the header information, you need to, on your server, allow other origins or other domains to make requests to your server. And this is what Discord does, and Facebook does, and Google does. so that you can make requests into their services. They set up the server side. This is obviously so that you can't just blindly fire requests at remote servers. This will work here when we build things locally because everything's going to run on localhost or 127.0.0.1, which is the universal kind of, your local machine always gets that IP address, right, as an alias. So once we start communicating this way, we're going to start sending information back and forth. So that verb, post, get, put, or delete, again, for almost all the stuff we're going to do, we're going to be posting stuff. The browser starts up, it does a get, a get, a get, a get, a get. JavaScript starts to run. You're going to then do whatever your app needs to do. At some point, your JavaScript is going to post a request to a server, and at some point in the future after that, it's going to get some response. And then you're going to deal with that response, right? Right. Now, some of the data that we send are going to be for getting or sending data files back and forth. One of the things I'm not going to dive too deep into is like uploading files. When we start playing with forms and inputs and stuff, you can actually upload a file from your local machine, right? The browser's not allowed to see your hard drive. It's another security thing. That's because otherwise I could write JavaScript that could wipe out your hard drive. And people would think that was bad. So the browser and the JavaScript engine aren't allowed to touch your hard drive. So the only way you access it is that there's a form element that lets you select a file from the hard drive. So the user has to select it. And once you select that file, what do you do with it? Well, that's up to your application on the client side. What you do with it, right? The headers, the information that we send back and forth, ideally we don't want to have to mess with that either, right? I mean, there are some defaults, and the tools we're going to use to send messages out to our servers are going to set up some default headers. So for the most part, we want to just use those headers as is. We don't want to have to mess with them to play around. It's not until you start doing some more complex server stuff that you really have to anyways. We may hook up some stuff on the server side to enable things, and this is typical of developers. What I'm getting to here is typically as a developer, you build everything in a sandbox on your local computer and you turn all the security stuff off. Because if you're doing some network programming and communication, to not know whether it's the security thing that's preventing your communication from working or your code broken is really frustrating, right? So by turning all the security off, IT guys do this, by turning all security stuff off, you know that anything that doesn't work is because of your code. Okay? Once your code works, then your job is to start layering in that security stuff and make sure it still works or continues to work. Told you I'd tell you what REST stands for. Representative State Transfer Protocol, which is a fancy way of saying that every request is independent from every other request, meaning every request has to have 100% of the information it needs every time you make it. Even if you ask for the same thing 6 times in a row, you have to provide all of the parameters you need. Now, if you bring up Google and you do a search for REST, let's say, what I'm interested in, let's grab that one. Just search for REST. I don't care about the results. What I want you to look at is this at the top. This is a request. That's a GET request. And that's what I mean by the parameters that get sent with the GET request are open text. Anyone can see them. This particular thing says, here, I've got search, and then it's followed by this question mark. That's the delimiter we use between the URI, or the resource indicator, and the parameters. After that, the parameters are all listed in an attribute equals value pairs, separated by an ampersand and sign. So what do we got here? Next parameter. What is REST? And no spaces, so Google puts pluses in. Right? The next parameter, any guesses? Do you know? Not for sure. Okay. This is Google's request, so Google can make that anything they want, that parameter. I can tell you that my guess is that that's my user ID. That's a hashed code for identifying me as me, because of course Google wants to track my history of everything I'm searching for.
Yeah, show personal, like, person, another word, like, for you and for me, it would be different, yeah.
Yeah. And it's an encrypted string that they make up with some algorithm. And that means that they can decode it on the server because they can decrypt it. Right? And how much information is baked into there, I don't know. I'm pretty sure it's just the user ID. Original question. What version of Chrome am I running? And again, they're just making up these functions that generate these, what we call hash values. Next parameter. From Chrome, using the ITF-8 character set, so that they know what I'm asking for. Okay. Now, the reason these parameters are this way is that original Apache servers running PHP have some nice functions to pull those parameters apart. As we stopped using Apache servers, we didn't want the internet to break. So as certain sites use Node servers versus Apache servers, they still take parameters the same way. So it's up to us when we're writing a Node server versus an Apache server. Hey, we don't have PHP, but we have our Node server, and so our Node server has to pull these parameters nicely. You know, the key for us using Node is just because we didn't want to teach you another language. Because otherwise, in order to do the web stuff, and when we first started teaching this program, it was HTML, CSS, JavaScript, PHP. It gets a little C#, C++, Python. Right. So we're getting rid of a couple languages by using the Node server. We can just use JavaScript on the client and JavaScript on the server. It also means your JavaScript gets better. Right. Coincidentally, what we're going to do with our JavaScript is the kinds of things that Unreal and Unity do behind the scenes for you. So if you understand how we build the applications as we build them in JavaScript, you'll also get a better understanding of what Unity and Unreal are doing behind the scenes that you can't control, because you're going to have to build those things yourself in our JavaScript apps. All right. Now, when we send this information, we're sending it as text, and we send it as text so that the person writing the server doesn't have to be the same person as wrote the client. This is a interoperability part. If I'm writing the server, I can write it in anything I want, whether it's a Java application or a Python application, because I want to do some machine learning stuff, and Python seems to be the language of choice for most of that these days. Or an old school PHP server I want to talk to, or a Node server. I don't have to know how the server is run or how it's built. I want to send text. I want to get text back. And that way I can write the server and the client in different languages, right? We like to write them in the same language because it's just easier for us because we're writing both halves. Out of all of this, you know, you will hear some of these job descriptions too. Okay, when we talk about web developers, you kind of break them down. front-end developers, back-end developers, and full-stack developers. Okay, front-end developer builds what's in the browser. It's the client application, JavaScript, HTML, CSS. The back-end developer writes what's on the server, mostly databases and either JavaScript in Node or Python, Java, or PHP. And a full-stack developer does the whole thing end-to-end. Right? The full-stack developers get paid more, by the way, like a lot more. Something about asynchronous communication that people think is difficult. Right? So we talked about this. You get, now I can use a timing diagram to kind of illustrate it here. So if you were to follow it through here on the browser, you type in a URL, right? That's that message getting sent to the browser. The browser then sends this get URL to our server, which goes and fetches index.html, which returns it. Okay? I don't have to put any names on that. I'm just putting arrows in to show that it returns it. And from here, I parse it. Okay? And in the middle of parsing that HTML file, I go get style.css, which it fetches and brings back to me. And as I'm parsing it further, I get my JavaScript file, and I bring that all the way back and parse it as well. So that's the 3 separate GET requests that get triggered automatically. If you have 4 CSS files, you got to trigger 4 of them. Right? Inside the CSS files, every URL function that you use to fetch image is another GET request. Okay? You can see them if you want to see them. When you bring up the inspector for your application, there's a network tab. The network tab, go into the network tab and then reload your browser. And you'll see all the requests happen. Right? And it'll also break down for you how much time it's spent processing the request and how much time it's spent waiting. And the waiting, you can't do anything about. You can't make the waiting faster. It's just a network kind of resource hiccup.
What is this waterfall thing here to the network?
Let me bring something up and we'll.
Okay, so it's specifying types.
Big enough to almost read. Is that the order that my HTML asks for them? Not at all, right? The hell? Well, that's that asynchronous part. You will notice because I use modules in here, index.js got loaded and then quite a bit later these guys came in as they were needed. And it'll give you the timing. You can really drill down on this. We're not going to spend a huge amount of time doing the performance side of things. You can zoom in, move this around. Just want to look at that. You look at just the fetch time. Just open it up. JavaScript files, CSS files, image loads. Right. And the little waterfall that you're talking about is this guy on the side, you mean? So as you hover over them, so it tells you what the different color things are. So tells you about queued for 7 milliseconds, request was sent, waiting, content downloaded. Now, I'm running the live server, which is local, so you would think there isn't a lot of wait time in there. So 100% of this is content download, transferring the content from my hard drive to the browser. Okay. If you start looking at these in depth on some public site, because you can bring up this inspector on any old site, what you'll see a lot of times is these big wait bars for things that you're like, why is that taking so long? Particularly if you open up a website and it's taking forever to load. And then there's a million different things. There's a whole course we could do on how do you optimize this stuff. We start talking about above the fold and below the fold and image optimization and placeholder images. So you download a small, tiny little image and you stretch it big. And then as the rest of your page is loading, you load a big image and you replace the image and all sorts of things for performance. The performance side of things we're largely going to ignore, mostly because we're going to be running so fast that it doesn't really matter. And until we get probably into term 4, maybe. All right. So some of the things that we have that are nice with this kind of a system, there's no limit to the number of people that can request things from my server. It's up to the server to throttle that. So if we've got a big server that can handle lots of requests, well, great. You know, typically when we're talking about these kind of requests, they don't come super fast. They come in little bursts, which gives each of our servers the ability to respond to those things. And so scalability when we're building games and applications around this is really pretty large. If you're building, like I said, a client server type game where you have to have live networking going on, things like a game server, you're going to have entire clusters of servers. If I've got a Core i7 here, maybe in a Blade, I might have, say, 6 or 8 virtual software servers on each CPU. And I've got 8 CPUs on there, or 16 CPUs, so I can kind of gauge how many people I can play off one physical piece of hardware. On the web side of things, though, because those requests come in these little bursts, I can actually handle a whole lot more people because I'm doing things infrequently and I've got longer time between requests and stuff. So typical kind of server scaling, you're talking about hundreds on a live game service, whereas on the website you might be talking about tens to hundreds of thousands. Now, the reason this matters when we're making games is part of our game design might hinge on it. If I'm building a Clash of Clans style game, I'm going to take advantage of that. The reason the game itself is asynchronous is because it's a web game. So all of the cities that you build are built in a client. And every time you build something, we send a request to the server to update a data structure. Every time someone attacks your city, they're just downloading your data structure and playing the game locally and sending the results back to the server. So there are these kind of like bursts of infrequent activity. It means we can have a large number of people playing the same kind of game at the same time. I like to use Clash of Clans because there's like 4 or 5 clones of it. But if you look at the top 20 revenue generators in the App Store, whether it's the iOS or the Android App Store, you'll find that they're these style games. Right? Biggest revenue generators. And they're all free. So they use this kind of system and terminology and technology. I've got another version of the same thing here. that represented on REST APIs or RESTful APIs, is just a fancy way of saying you got to send everything every time, right? When you're in the service side, that means you have to write a little bit of code to extract everything you need from the request. So that's going to take a little bit of work, but as we see next term, we're going to write the first one in the first couple days. And we're going to link in some third-party tools to help us pull this stuff apart so that we don't have to write everything from scratch. I've already played with that thing. This is just a list of some of the headers and stuff. All this header information comes with every request, so if you need it, you can extract it again on the server side. But that's the nuts and bolts about how header or how servers work. The next term, I'm not going to go into a ton of how they work, other than we're going to kind of like configure, build, and set them up pretty quickly. I'll introduce you to the projects we're going to build for next term. Next week sometime, week after that. Right. And then you'd be like, wow, that's so cool. And then you'll start thinking about how the hell are we going to do that? And then you'd be like, oh yeah, that's no problem. Then you're going to start writing it, and you're like, I have no idea what's going on here. It's usually the pattern I see.
Yeah. Kind of.
All right. And that's it for this topic, and that's it for today. You got some time to work on your Minesweeper if you want. If you have questions, David and I are here. Right. Don't forget, you can bug us, especially via Discord, anytime.